Hey everybody, this is example number 2 for structural analysis of deflections using the conjugate beam method. And the problem statement that we have is we're asked to calculate the slope and displacement at the free end, point A, using the conjugate beam method. And EI, Young's modulus times the moment of inertia, is constant. So here's our cantilever beam. Our free end is A. And this is where we have our concentrated load of 5 kilonewtons, which we'll call P. And the fixed end is B. And the total length is equal to 5 meters, which we'll call L. So the first thing we're going to do is calculate the reactions at the fixed support at B. And so the vertical reaction at B is simply equal to the load P. This is just using basic statics. And the bending moment is equal to the concentrated load times the moment arm, which is equal to the beam length since the load is placed at the end. So the moment is equal to P times L. Now we're going to construct the M over EI diagram, the moment divided by Young's modulus times moment of inertia diagram. So here's what it looks like. We have the maximum absolute value is equal to negative PL over EI at the fixed end, and it goes to 0. It goes to 0 at the, let me see what we labeled it again, A and B. So at A, the location of the concentrated load, it goes to 0, and at B, it's negative PL over EI. After this, we're going to construct the conjugate beam. And so our real beam, let me just clean this. Our real beam is, we have the at point A it's free, and at point B it's fixed. And so the conjugate beam is, it's going to be fixed at location A, and it's going to be free at location B. So we call it A prime and B prime. And each support condition, whether it's fixed or pinned or a roller, or if it's free, each support condition, there's a real condition and there's a conjugate condition. And you can find a chart for this in your structural analysis book, and they'll show you a support condition and show you the real case and then the corresponding conjugate case. And then also on this conjugate beam, we're going to overlay the M over EI diagram, which we can consider like the conjugate loading. And because it's negative moment, it's going to, and because it's negative moment and it's below the beam, it's important to make sure that the load, that this M over EI diagram is, the arrows are pointing away from the beam. If it was positive moment, this M over EI, this conjugate load, would be pointing upward, again, away from the beam. And so since in our case we have negative moment and negative moment, so it's pointing down and away from the beam. And so our value here is negative PL over EI, and it's 0 at this end. So now we're going to calculate the slope at the location A. And so to find the slope, we just have to get the shear value. We have to calculate the conjugate shear at that location on the conjugate beam. So it's just going to be using basic statics. So here's the simplified version of this beam. So we have our shear at A, bending moment at A. And then we take this whole conjugate loading, this triangular loading, conjugate loading, and we simplify it. And since it's a triangle, we're just going to use a formula for triangle, base times height divided by 2. So it's going to be equal to PL over EI, which is the height, times the base, L, divided by 2. And the centroid acts at the third point, so it's somewhere over here. So this is equal to L over 3. And so that's how we got this value of L over 3 and 2L over 3. And now we're just going to use statics and calculate the shear at location A, the conjugate shear. So it's the conjugate shear at A minus PL squared over 2EI. So that means the shear is equal to PL squared over 2EI. And now, so the slope is also equal to this value. So the real slope is equal to the conjugate shear at that location. And now we just plug in the numbers for P and L and EI. And EI was constant, so that just stays. So 5 times 5 squared, so that's 62.5 kilonewtons times meter squared divided by EI. And that's the slope at A. And now we're going to calculate the displacement or deflection at A. So to calculate the deflection, we have to get the conjugate bending moment at that location. So let's go back to our figure. So the moment arm of this conjugate load is equal to 2L over, it's over here, 2L over 3. And this load is equal to PL squared over 2EI. So again, using statics, we find an expression. It's negative moment. So counterclockwise is positive. So negative conjugate bending moment at A minus PL squared over 2EI times the moment arm of 2L over 3, which means that our deflection at A, should be A. The deflection at A, which is equal to the conjugate bending moment at A, is equal to negative PL cubed over 3EI, and we just plug in the values for P and L, and that's negative 625 over 3EI. And this is the end of this example. Please subscribe to the channel. Check out the Facebook page. It's facebook.com/EngineeringExamples. And also please visit the website. It's EngineeringExamples.net. Thanks. See you guys in the next video. Thanks.